Alright, so before I get into the example, I want to make sure that we understand kind of what's going on with each of these three equations, okay? Because there's not special equations for projectile motion. We just manipulate them according to the gravitational constant, and we just have two axes this time. We have x and y. But most commonly are going to be these three equations, because it's really the y-axis that's complicated, because the y-axis can go up and down. So this first equation here is really just going to explain what the velocity is on the vertical axis at any given moment. So if we know time, then at any moment we can find the vertical velocity. So we can determine whether or not the projectile is moving up or down. If we know time. If we know time, everything is easy. Okay, the next one is honestly probably the most important. And with this one, this will tell you the vertical position of the projectile at any time. Okay, this last one is going to be used most commonly in the beginning to determine things such as the maximum height. So with this, it's essentially vertical velocity dependent on position. So this is if you don't know time. And generally you will use this to find the maximum height. Okay. So let's take a look at our projectile motion graphs. All right. Okay, so let's actually start with a vertical displacement versus horizontal displacement graph. And this will basically be used to tell us the position of the projectile at any moment in time. Okay, so essentially this equation will always be used to determine where the projectile is up or down, its vertical position, where this equation writes there's no acceleration, so it simplifies to this, is going to tell me where the projectile is, left or right, so it's horizontal position. Okay, now when you graph this for any projectile motion, it's going to look parabolic. Okay, so it's going to look like this if it's for something that lands at the same height, which if you're in an advanced math class you should kind of be able to tell because of this negative t squared quantity. Okay, so using any of these equations, if we were to pick a random point, Oops. And we know its x and y coordinate. Okay, and we know the initial velocity, then we can solve for time. Okay, so that's one graph that we should be familiar with. Okay, the next graph that you should definitely know is the vertical velocity versus time graph. Okay, so let's kind of reflect here that the slope on this velocity graph will equal to acceleration. So this must be equal and always equal to g minus g, so minus 9.8 meters per second squared on Earth. Okay, so in general, you're going to get something that looks like this. Okay, so this, it's when it's moving up. This is at the peak. And on the bottom part, it means it's heading down. Okay, so rising and falling. Okay, so the acceleration graph is just flat horizontal. Okay, so this equation is going to be used, think of it as like on this graph, it's going to tell you what the velocity is at any moment in time, if you know time. Okay, so if you want to know the velocity at this time, plug in time, you know g, you'll know the initial velocity, then you can find what the velocity is at that moment. Okay, I don't want you guys to get hung up on the zeros here, okay, because it depends on the segment of the problem that you're looking at. So yeah, if you're looking at the point in the problem where it's rising, this will always be the initial. But if you are looking at the part where it's falling, then this part will become the peak. Okay, because you can only evaluate things really from looking at 2 points. So this would change to the peak. Okay, but this equation isn't that useful when it changes to the peak, because usually when it's falling, you want to find out the time, and this equation won't help you there, because you're going to be left with only one velocity quantity. But it's useful to know what the final velocity is when it hits the ground. So that's usually what it's used for. Alright, and the last graph that I want us to really look at is the horizontal velocity graph, and this just shows that it's going to be constant due to time, over time, and when we finish problem 3, we're going to reflect back on these graphs and kind of put some points on them. So the next thing to do is to find our x and y components. So what I like to do is make a triangle with my components. This is the hypotenuse, 35, and then there's the x component and the y component, 90 degrees and a 70-degree angle. So our x component is 35 meters per second times cosine of 70 degrees. Comes out to be basically 12. But I did my math with this number, so I'm going to keep it like that. And the initial y is just the sine. And this is 32.89. So almost 33. Okay. So let's look at the question. So the question says, what is, with this initial speed and launch angle, how far away from the wall should the trebuchet be to hit the top of the wall? So I want to rephrase that to say, to make sure that it hits the castle on the way down. So how far away should it be for the projectile to hit the castle wall when it is falling? Okay, and the reason why I want to do that is there's really like two main scenarios that we need to look at. Scenario one is that it goes like this, okay, where it goes up, reaches its peak right here at the top, okay, and then falls back down and hits the wall. The other option is if we have the wall, the castle wall, and the projectile just goes and it goes and hits it right on the way to its peak or at its peak. And so this is going to be scenario 2, which I'm going to change to be kind of like the second part of the problem. So we're going to have a much shorter horizontal displacement for this one, right? Because it's going to be in the air for less time. Okay. So let's change the question to say that it hits the castle on the way down. Alright, so we can see that I have my vector triangle here with Vx and Vy. So we already broke those into components, which is good. And really the main thing about these types of problems is making sure you break it into two parts, into rising and falling. And I can't stress that enough. Okay. Right? If you know it's going to hit the top, hit its peak, and come down, you know, like, you can't just solve everything with one step. Okay, so why? All right. All right. I wish I could make a graph kind of here. Okay. So this is kind of my origin here, because the green dot is the projectile. Okay. So basically, that's y0, and this is x0. Okay, and y1 is going to be here at the top, where x1 is, and then x2 and y2. Okay, if this doesn't make sense, then let's go back to this graph. Because this is basically what this problem is doing. This problem is basically having us launch at some height, and it's going to stop, you know, somewhere in its arc about here. Okay, so I think maybe if you think of it as kind of a chart or a graph like this, it might be easier to think that every position here is going to have an x and a y component. Alright, so this is x1, y1, and this one here would be... Okay, does that make more sense? This is the peak. This is where it lands. Oops. and this is where it like launches from. Okay. Okay, so I've revised the question to tell you that the ball is going to go, that the projectile is going to go up and start coming back down. But, what if you didn't know? How would you find out? And this is really where those of you who attempted the question, made a mistake here. And it's because I think a lot of you guys were using this equation, and when you're using this equation and you plug in 0 here, if you plug in 0 meters per second there, that's going to tell you you're going to be able to solve for the time until the peak, so the peak of its motion. Okay, so but you have to understand that just knowing a time can't tell you a position without using that time to find the position. So how do you know where the projectile is at that moment after you find the time? Then why don't you put it into here and see where it is? Okay, so we can go ahead and find the time to the peak, or the T rise. And this whole part here is going to be the rising portion. Okay, so I already highlighted that equation. So 0 meters per second is equal to 32.89 meters per second minus 9.8 meters per second squared times t. Okay, and in the beginning I will show you every algebra step, but I hope for us to be able to do algebra faster, basically. Okay, so in that equation you'll get that T rise to 3.36. Okay, so that's the time until the peak. Okay, so the next thing you should ask yourself is, how high is it? Okay, so in order to determine how high it is, since we know the time to the peak, we can either use this one that I highlighted in green, or you can always use this one, okay, because you know the launch, the launch velocity, and you know the velocity at 0. So it doesn't matter. Okay, it really doesn't matter. But since I already know time, I'm going to use the second one. So y1 is equal to y0, which we know is 5 meters, plus by0 times that t rise minus 1/2 g t rise squared. Okay, so this is 32.89 meters per second and 3.36 seconds minus 4.9 meters per second squared times 3.36 seconds squared. Okay, you will end up getting about 55.19 meters. Okay, maybe a little different due to rounding. Sorry, since you are adding in that 5 meters, basically this quantity here will be 55. And then we add that 5, so it's 60. So that's above the ground. Okay. So, I'm not really sure why there was so much confusion here. But what this is telling you is when it hits the peak, that's how high it is. So, you know how we were saying x0, y0? Basically, our first coordinate was 0 meters, 5 meters. This one here, well, we haven't found x yet. We don't necessarily have to, but we know that this is basically 60 meters. Okay, and we don't know these two yet. Okay, so since I know the horizontal velocity, I can find out, you know, where along the x-axis it would be, right? Because remember, we're looking just at like this type of coordinate system, y versus x. Okay, we have to know where it is before we can proceed forward. Okay. Alright, so now that we know it's at the top, what should we do? Is there anything else that we need to find while it's still rising? Not necessarily. I'll say that since we already talked about x, we can go ahead and solve for it. So basically the delta x here is x1 minus x0, and that's just going to be that 11.97, which is basically 12 times 3.36 seconds. You get 40.22 meters. Okay, so this is basically 40 meters. So after 3.36 seconds, it's moved 40 meters to the right and 60 meters up. Okay, does that help? Okay, so now considering it falling down. So one thing that we should think about this conceptually is it's going to fall for less time. And the reason for that is it has less less of a height to fall, basically. It's not falling the 60 meters, right? So going, so let's say this. The time, like for example, the time to rise for a projectile, 20 meters, is equal to the time to fall, 20 meters, right? They're equal. Right, so if we're looking here, well, this particle, projectile, I keep saying particle, this projectile rose about 50, well, yeah, basically 55 meters. Well, if this is 60 meters and we know it's got to land at 30 meters, it's really only falling 30 meters. Okay, so that means that I know that the time to fall is going to be less than the time to rise. Okay. Now, this part should be very easy. This is just free fall. treat it just like free fall. So we know Vy1 is equal to 0 meters per second. Okay. So if this is equal to 0, the equation that you're going to want to use is this. T squared. Okay? Don't be intimidated by this equation if this is equal to 0. Right? This is equal to 0, so it's not an intimidating equation. You don't have to worry about quadratic formula. Okay, we're looking for t. It's all the way over there. Okay, so let's go ahead and subtract y1. We have our delta y over here. And this is equal to negative 1/2 g t squared. So let's go ahead and divide by minus 1/2. This is equal to gt squared. So divide by g. That gives us I don't know why I wrote minus 2. Okay. Alright, so now I need to do my square root on both sides. Okay, if you were wondering, if you were scared about that negative sign, don't be scared, because y2 is 30 meters, or y1 is at 60.19 meters. Okay, so this quantity here will be negative, and this is negative. That sign will go away. Okay, and I wrote t squared again. Alright, so t fall. Get 2.48 seconds to fall. Okay, so once again, once we know the time, everything is easy. Okay? So let's find our total time. And I think maybe that's where some people were getting confused. That when we're starting the time, we're only considering, like t fall, remember, is only the time to go from here to here, horizontally. And it's only the time to go from here to there, vertically. So it's only a portion of the entire process. So we need to find the total time. So that is 3.36 plus 2.48 seconds. And that is equal to 5.84 seconds. Okay. So now that we know the total time, remember this equation underlined in purple, the middle one, that's going to tell me where the projectile is vertically at any given time. That's what I'm going to use. Okay, now that I know the total time. So what is, so we're checking, this is basically a check to see what y2 is equal to. So y2 should be equal to y1, which is our peak, and then plus 32.89 meters per second. Seconds minus and then 5.84 squared. Alright, and you'll actually get very, 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 very close to 30 meters. Okay, it's not going to equal exactly 30 meters due to rounding. Right, we have rounded this number, we rounded this number, this is due to rounding, you know, this right here, we're squaring a number that's been rounded, so it's a little bit over 30 meters, but it's very obvious, we can tell that our answer is correct. So what is the position then? So this is the final part. How far away is it? Well, now we just need to find our 11.7 meters per second. And I made a mistake. This is for the, we want to find the total distance that it moved. And we get 69.93 meters. Okay, so going back to my picture. This is basically 70, 69.93, basically 70, and this is 30. Okay, so if we were to plot these points, right, it's going to look just like our graph here. Okay. All right, everything checks through. Right? You can check everything here. So let's do an extra step. Let's do like a bonus graphing part. I mean, who knows? You might have to graph something coming up on the test. Hint, hint. Okay. So what if I said graph v of x against time? I need to make this a little bit bigger. I apologize for this not being completely straight. It's kind of harder than you think. Okay. 1 second, 2 seconds, 3, 4, 5, 6 seconds. Alright, and what was our velocity? It was basically 12. So let's call this 6. We'll call this 12. And 5.84 would be a little bit past there. So, yes, that should be a straight line. I don't have full control over that line. So yeah, it would look like that. And what about our y? What would our y look like? So the y one is definitely the most important one. One, 2, 3, 4, 5, 6. Okay. One, two, three. All right, and our initial velocity for y was almost 33. So let's see, 1, 2, 3, 4, 5. We could just label by 10. That's fine. Okay, that's good enough. So let's go ahead and put a point here. Oops. 32, 33 would be right. Nope, would be in the middle of these two. No. There we go. Alright, that's my first point right there. And let's reflect back. Where was it equal to 0? Where did it hit the peak? It was after 3.36 seconds. So at 3.36 seconds, which would be about right here. Okay. All right. Should you take the time to find this velocity? I would say if it's on a test, no. I'll show you what I would do. Okay, so if you're rushed for time, this is what I would do, and we'll kind of check this afterwards. We have 2 points here, and it might be, honestly, might be really tough with this app, but we're basically going to attach these two if it wants to work, and I'm going to bring that line down to our 5.84 seconds, so that's going to be it's going to be a little bit shorter than that, but that's pretty close. Okay, if we wanted to check, we can check to make sure that slope is equal to negative 9.8. Okay, so if we wanted to check, we would simply do, well, we could go back to this equation, and I would just do it from the peak, and then minus G, and then this would be T fall. Okay, we're in that portion there. This is basically minus 9.8. And this is times 2.48. So this will be minus 24.3 basically. Alright, so let's reflect on our graph. Our graph approximates basically right at 24. Right? Because each cube would be 2 meters per second. So that's very, very good. Right? We should be happy. That's very good. Awesome. Okay. Now, to be honest, the last part, it will not work. Okay, I can show you how it would work, but it's going to be about 8 meters short. So I think instead I'm going to change the angle. But before we do that, I want to do the other scenario where it hits while still rising. This is good to know too. Definitely study that first part. It's very kind of common to be tested that way. Now with this scenario, let's think of it that, well, we already have the knowledge that if the castle wasn't there, this would continue to rise. Okay, but the castle is there and it's going to prevent it from rising because it's going to hit something. There's going to be a collision. So with that knowledge, you're going to know that velocity right there is not equal to 0. It still wants to move upwards. Okay? So we cannot just blindly go through these equations without thinking about what is going on. Okay? We're only using the same 3 equations. We just need to do a little bit more thinking and understanding the situation. So, what do we want to do? Can we, we still know that y1 is 5 meters, and we know that y2 is 30 meters. So we know that difference is 25 meters. Okay. So we need to use this information. Okay? I cannot just use this equation right away. Because I don't know time. Okay? I can't, and I meant to write a 1 here. Sorry. I need to make the eraser smaller. No. Okay, that's equal to 25. So I can't use this velocity equation yet. And I can't use this yet either. Okay, both of those require time. And yeah, but I know the height. I know this. This is valuable information. So I'm going to use this. I wish this was like my board where I could just move it down. Okay? But luckily, since we are solving for this, right, we know the difference in height, and we know gravity, we know the initial velocity. This is pretty easy. So Vy1 is equal to the square root of Vy0 squared minus 2 times G times Y1 minus Y0. Okay. So 32.89. All right, get 22.14 meters per second. So it is still moving up. If we want to go back to this equation, okay, if we start at that red line, it's going to be basically somewhere around here. Okay, yes, it's slowed down, but it is still moving up. Okay, so what am I going to do with that information? Well, I'm going to go back to our velocity equation. So I'm going to go back to this one, because now I know both quantities. I know this, I know this, I know this, so I can find time. So what is this time going to be? In this case, this is going to be the time to rise. Okay, so T rise will end up equaling 0 minus 22.14 meters per second over minus 9.8. And this is a pretty small number, or relative, 2.26 seconds. Shoot. I'm sorry. I wrote this down wrong. This is 24. .33, and this is, yeah, I thought it was a small number. I'm sorry. Looked at the wrong part. This is 0.87 seconds. So a very short amount of time. And so, what is that position? So in this case, T rise is the total time, right? So 11.97. So it's just a little bit more than 10 meters. All right, but let's think about it. If this was a real war scenario, would you want to be this close to your enemy? I wouldn't want to be. I don't think the Trebuchet would be very effective at that range. I think at 70 meters it would be a lot more effective. Okay, so finally, I want to solve the last question as intended. Sorry about that. We are not going to solve it that way. It's not really necessary, and it's pretty involved, and I think we covered a lot right now. And I think these two scenarios here are really what I wanted to get across. So I know this is long, but I hope this really helped. Please at least skim over this for the test. Thank you guys. Bye.